This is Sam Ziss from Dr. Epek's Thermodynamics class. Today I'm going to be solving an original problem that I wrote for chapter 4. We'll start by reading the problem statement. It says, calculate the heat in kilojoules per kilogram transferred to air in a rigid container with an initial temperature of 700 degrees Celsius if its pressure changes from 173.5 kilopascals to 120 kilopascal and the room temperature specific heat for air is used. Just jotting down some of our information here. We were told to find the heat, and the reason I write this as a lowercase q is because if you look at those units, kilojoules per kilogram, this is really a specific heat that they're asking for, so I call it a lowercase q. I see this word rigid, which tells us that the volume is not going to change or that V1 equals V2. We were told a temperature T1 equals 700 degrees Celsius. I'm going to go ahead and convert that to Kelvin by adding 273 to it so that our initial temperature can be written as 973 Kelvin. Similarly, we were told an initial pressure of 173.5 kilopascals. Later on, we're going to need this in megapascals, so I'll divide by 1,000 and get 0.1735 megapascals. Similarly, our final pressure can be written as 0.120 megapascals. Alright, continuing with this problem, we were told that the substance that we are working with is air. And whenever I hear air, one of the things I want to look at is to decide whether we are dealing with an ideal gas. Because if we are, there is a very simple equation that we can work with. So we're going to go ahead and decide whether we have an ideal gas by comparing our initial temperature with the critical temperature for air. What we want is to see that our temperature is greater than that critical temperature. That needs to be true, and our initial pressure needs to be less than the critical pressure for air. Our initial temperature is 973 Kelvin, and our initial pressure we wrote as 0.1735 megapascals. We then go get these critical temperatures and pressures from a table that I have saved here. Looking at this little chunk of table A1, we can see that our substance air has a critical temperature of 132.5. Notice that those units are in Kelvin. We wanted our temperature to be greater than that value, and it in fact is, so far we may still have an ideal gas. Checking the critical pressure, we see a 3.77 megapascals. We wanted our pressure to be less than that, and it is the case that 0.1735 is less than 3.77. So, both conditions checked out, we are dealing with an ideal gas, which gives us an easy equation to work with. We will come back to that equation in just a little bit. Again, keeping our goal in mind, our ultimate goal is to find the heat, or Q. And a lot of times when I hear that word heat, it brings to mind the energy balance equation, which I'm going to just jot down in its most general form. The energy in minus the energy out equals the change in the energy. I'm going to start with the energy coming out. We were told that this tank is rigid, this container is rigid, which means that our volume is not going to change, which means that there will be no boundary work here. So for the moment, I'm going to call our energy coming out 0. We don't really see any other work being done here, so all that we're going to call for the energy coming in is the heat. Looking at the other side, the change in the energy, this is a stationary system, which means the only total change in the energy is going to be the change in the internal energy. Looking at that capital Q, we have an equation for this, which says that M times CV times T2 minus T1 equals our capital Q. And there are several variables here that we do not have, but the one that's really troubling is the mass, because we don't have the mass and we don't know how to get the mass. Which at first glance is kind of a problem, but what we're going to do is actually just divide this over to the left-hand side of the equation so that it cancels out. And what we're really working with here is Q over M, the heat divided by the mass, which is really just the specific heat, or lowercase q. And the reason that we're really okay to go do this, to call it lowercase q, is if you look back at the problem statement, again, we kind of touched on this earlier, these units are kilojoules per kilogram. We are finding a specific heat rather than the total heat. So we are okay to just call this lowercase q. So our ultimate goal is to find specific heat equals CV times T2 minus T1. And out of these variables, the only one that we have at this time is T1. We can, however, go get CV from one of our tables. Table A2. This is that piece from the problem statement where it said the room temperature, specific heat for air is used. We can get that again from table A2. Again, our substance is air, and we are finding this value here of CV. So we now have CV. We can say that CV equals 0.718 kilojoules per kilogram times Kelvin. One more value to find, and that is T2. And we're going to get T2 going back to the fact that we have an ideal gas, which means that we can write the ideal gas equation. Which says PV equals mRT. I'm going to kind of write this equation twice, once for state 1 and once for state 2. For state 1, we have P1 times V1 equals mRT. For state 2, we have P2 times V2 equals mRT2. Sorry, I should have put T1 over here. And notice, speaking of those subscripts, we did not write a subscript, a 1 or a 2 for the mass or for the ideal gas constant, because those are staying the same. It doesn't change from state to state. With that in mind, we're going to isolate M and R on each equation, so that for state 1, we have MR equals P1V1 over T1, and for state 2, MR equals P2V2 over T2. what we can then see is that MR is in each of these equations, which means we can just set P1 V1 over T1 equal to P2 times V2 over T2. At this point, I'm going to pause just for a second and recall that our ultimate goal here is to find the specific heat, and in order to do so, we need to find T2. So I'm going to isolate T2 within this equation. We have rewriting that T2 equals P2 times T1 over P1. Substituting, I have 120 kilopascals times, now I'm going to hesitate before I write this temperature. Whenever you use the ideal gas equation, you need to use Kelvin. So I'll write my 973 and divide that by the 173.5 kilopascals. For the pressure, I could have used the megapascals. Those really don't matter though, because those kilopascals are going to cancel anyway. As long as you're using consistent units, those are going to work out correctly. Getting T2, we have 673.0 Kelvin. With this value in hand, we can finally go get our ultimate goal. We are looking for Q in, which was, again, the calculation is CV times T2 minus T1. We found CV to be 0.718 kilojoules per kilogram times Kelvin. Notice that this is written in terms of Kelvin, so we have to keep going with Kelvin. T2 is 673.0 Kelvin minus our initial temperature. T1 was 973 Kelvin. And we are going to get our final answer here, Qin, as negative 215.4 kilojoules per kilogram. And I just want to take a second to talk about the fact that this number came out negative. What the negative really means here is that if you go back to when we wrote the energy balance equation, when we said that the energy coming out was 0, we assumed that this energy was coming in. When we see a negative as the energy coming in, what we're really saying is that the energy is going out. Or, in other words, Q out would actually be positive 215.4 kilojoules per kilogram. Or in other words, this energy is leaving the system, or more simply put, it's cooling off. And that will be our final answer. Thank you very much for watching.